While several billion-dollar companies are racing towards Skynet, we're all left in the middle, no man's land, wondering what's going to happen and how long it's going to take until we have to sell our kidneys for a few more Starbucks tokens so that we can live just a few more days in the United States of Google. Well, I want to onboard this gravy train, or at the very least, I want to see some AI do some cool shit. I have no idea how it works, I have no degree, and I've never done this myself before, but I'm going to learn from scratch, and ChatGPT is going to help me do it. What I do have is about 10 years of amateur self-taught programming experience, and also the inability to give up on a project which is clearly too difficult for me. Enter GT Sophy.
The simplest way I would explain GT Sophy is an AI agent that learned to drive by itself at a very competitive level and is able to compete with the best drivers in the world.
GT Sophy was made over a couple of years by a lot of super smart people who know far more than I do. It also used thousands of PlayStations in the cloud. Now, I don't have thousands of PlayStations, I don't even have one PlayStation, and that means I can't enjoy GT Sophy. So, we're not going to buy GT Sophy because we're going to make GT Sophy at home. Instead of Gran Turismo, we're going to do this in Project Cars 2, and we're also going to apply a lot more restrictions to the goal of the model. You see, GT Sophy was taught to be competitive, but also to play fair. I'm not interested in any of that. I just want to see the car go vroom vroom real fast. So, let's forget about racing against other cars and just race alone. GT Sophy is also very well-rounded, so it can drive any kind of car on any kind of track, but we don't have until the heat death of the universe before Terminator 2 starts killing us, so we're just going to bring it down to one track, Alton Park in England. I chose it because it's very small, so we should be able to learn it relatively quickly. Lastly, we're only going to give it one car and hope that it learns to drive it really well. It's the Formula X, which is essentially a fictitious, overpowered F1 car. Without further ado, let's get started. Yeah, I don't do planning. Alright, so I guess we need some data, right? That's how you train a model. You get loads and loads and loads of data, and then you feed it to a model and it gets good at stuff. So we need to gather data from driving in the game. Luckily, there is an easy built-in way to do this. Project Cars, like other racing sims, allows telemetry out into a file. With some quick Googling, I found several projects on GitHub, all available for free, that allowed me to make use of this file. One of them I went with, which is called CarSaw, made by Matt Lin. Thank you, Matt Lin. In a wild true loop, we take a snapshot of the shared memory file that grabs one frame of game data. We check the time on that frame. If it's changed, then we take this fresh frame, we put it in our list. We can break this loop by pressing any key on the keyboard. Here's some code which takes an entire session and turns it into a CSV file with the help of the Telemetry Whisperer, then pulls it into the database. This is the Telemetry Whisperer class, which is just a class that understands the structure of the shared memory file. The first function goes through and gets a header row, so we know what the first row of the CSV looks like, and the next function gets all the data out of all the frames. It's ugly, but it works. Now the only thing to do is to drive and to fill the database with data.
Slid upside down off the track. There was chaos, drama, and a number of other phenomenal avoidances.
Right, so we still have a problem. We still need to be able to pass control input from Python into the game. So the library I'm using to do that is called PyVJoy, which is a Python library which interfaces with VJoy, which is Virtual Joystick, which is the go-to library on Windows to control HID joysticks. So this program is called X360CE, and this is the program which is going to offer a virtual device to Windows and make it available as a game controller. Something that looks like this, that we can program the triggers to be throttles and brake, and this to be the steering. So I've assigned these, and I've assigned it to the game. Okay, so we need to test to make sure this code works, and the simplest way of doing that is to just read in an old CSV file of a lap that we did, and get the car to replicate all of those actions. So let's just test if that works. And there we go, we have control and we are flooring it, a little headbutt into the wall. But then, as you can see, the steering does actually seem to work. But we do have an issue. You can see here at the beginning of the race that we are missing a slight left turn to adjust to the curve of the straightaway. That's what causes us to slam into the wall at high speed. and then we steer a little bit too early because we lost some speed from the impact with the wall. The reason this happens is because of this graph, which shows the input on the controller along the x-axis and the in-game steering value on the vertical axis. The blue line is the controller that I normally play the game with, which is a G920 Logitech wheel, and the orange line is our virtual Xbox 360 controller. As you can see, they have different steering curves, and this is partially down to settings and configurations, things like sensitivity and dead zone. So I turned off all the dead zones and put all sensitivity to a 1-to-1 ratio wherever possible. And that's how I found out that Project Cars 2 uses a dead zone for an Xbox 360 style controller, which cannot be turned off.
No! God, please, no! No!
This graph is a lap which is replayed into the 360 virtual controller, and you can see the problem a little bit more clearly. See down here with these small steering values which we just completely ignore because they're wrapped inside the dead zone, but outside of that we can actually use the steering wheel. But seriously though, I wasted way too much time on it. My essential plan was to come up with a function which when graphed would match the exact curve of each device. That way you could just take your input, your desired steering value, input it to the curve, and you'll get the corresponding value of steering which will get that result. This is really ineffective and inefficient. The biggest problem was that I was trying to use sigmoid or nonlinear functions to describe this curve, but this isn't a sigmoid function, nor is it nonlinear. It's just a linear curve that has a dead zone in the middle. And then, after a little while, I realized that even having a curve in the first place was a waste of time, because this array is a very, very small data set. Really, we're just encoding a curve that only has 32,000 points, so why not just measure everything and then store it in memory? That's only 128 KB. Google Chrome spits in the face of this curve every single time you even think about the new tab button. So here it is, the frozen X360 steering curve. We use CSV files to persist the values once we're happy with them. And when we want to get a given value of steering, we use a binary search implementation, which is up here. So there we go, that's pretty smooth. That'll do for now. At this point, it's time for what you all came to see. Enough about steering curves, let's train some AI. This is what I asked ChatGPT for. It gave me a small version with 4 layers, 128, 64, 32. And every model has an output layer of 3. That's because we're predicting these 3 controls. So that has to be the size of the output layer. But we have a small, and we have a medium, and we have a large. The loss function is mean squared error. Epoch count is 10. That's how many times this is going to see the whole data set and train on it. Batch size 512. I'm implementing early stopping, which means that if the model stops getting better, then we're wasting our time to continue, so we just stop the training there. The final piece of the puzzle is the data that we're going to train the model on. So let's not get into this too deeply, but this basically creates the description of every single sector that we have where we didn't crash. We have 1.4 million rows of data.
Watch a movie, take some pictures. I'll pay you.
Small model, 1.4 million rows of data trained, 10 training epochs, batch size 512. Here we go. Wow, that's interesting. Okay, that's a new one. I haven't seen that one before. That's a really interesting driving style app. Wow, we overheated the front tires on grass. Okay, yeah, I'm gonna go ahead and call this one. Well, so that was that. What about the medium model? Okay. immediate kamikaze into the wall. And look at those mirrors bounce. Look at them jiggle. Okay, I'm gonna go ahead and call this one too. Wow, that was violent. Okay, we've created the Ken Block of F1 drivers. It's a very even circle, actually. But I'm going to go ahead and say it's not going to be a lap record. So the models don't perform particularly well. This is the data that it has access to every time it makes a prediction. And there is no information on this screen that tells it that we're on a straight that curves slightly left. It has no perception, it can't see what's in front. So what decisions can it make? Here's how GT Sophy does it.
The local inclination of the surface of the road, so it could tell if it was going up or down a hill. The car's orientation with respect to the course centre line, which is modelled with respect to the left, right and centre lines of the track. A set of course points, which is broken up into 60 chunks of equally spaced 3D points on the left, right and centre line, and in fact all 60 chunks are modelled at each time step relative to the speed of the car, so it can always effectively see the track it would come up against over a period of several seconds in front of it.
So we do have orientations already, but we're going to have to engineer the other two from scratch. That's what we'll do in the next video, as well as deep diving into how to make the models actually good, optimizing them, choosing hyperparameters, and also working on the data to increase the data size. I have a Patreon if you'd like to check that out, and to my one patron, Nils Hagner, I'm sorry bud, you came for the VR gaming videos and I hope you'll stay for the programming, but if you don't, I understand.
No!